So here we are coming on the back end of the notes for this lesson. And so here we have some more interesting things. They're going to keep getting, more interesting, more complicated as we move through. But again, I don't want you to lose your perspective here that generally, you're going to handle a lot of integrals in this class, and you're not going to know what kind it is. You're just going to have to diagnose your problem. And on a lot of things, yes, I want you to think, hey, is there any algebraic way out of this crisis? There's no quotient rule for integration. That's off the table. There is no way I can clean this up. I can't simplify it. It is a proper fraction. We talked about what improper fractions look like in integrands. The degree of the numerator is smaller than the degree of the denominator, so there's no long division needed. We really don't have a lot going on here. What I could try to do is I could try to say, let me try a basic u sub where I let u equal the entire denominator. And if I do that, what I'm really going for is I'm going to try to morph this integral over to be 1 over u du, right? So that's my goal. And chances are this has a shot because I see the derivative is going to be some kind of linear expression. And I see a linear expression in the numerator. So I'm going to go for it and I'm going to do it. Once I set the u, I always do the follow through. And then I'm actually going to solve this for dx equals, which means du divided by 2x minus 4 is dx. Okay. Maybe I'll even clean that up. What is that? That's really, I could take out the GCF of 2. I don't know, just kind of cute. I'm recognizing that. I'm going to do that. Now, I'm going to morph this over, right? I'm changing my integrand from the x variable. I'm doing a basic u sub. I didn't really mess with the 6x minus 12. I kind of ignored that straight up. But I let the entire denominator be u. And now I have a follow through for dx. dx is going to be replaced with du over 2 times x minus 2, which doesn't necessarily cancel, right? I feel this isn't quite great. But if I come at this and realize, hey, I can factor out a 6 from that expression in the numerator, well, now this is awesome because now I have something that's legally cancelable, right? I can legally slash out that common factor of x minus 2. That's great. And I'm not going to be bothered by the 6 and the 2. They're just numbers. They're going to combine and kind of come out here as a 3. And you have accomplished your goal. So there's a lot of integrals you're going to do, and you're going to weave your way through all of the strategies from Calc 1 and the new strategies from Calc 2. It's very often that you see just a regular old Calc 1 integral work its way into a Calc 2 problem. So this is really important stuff. Now you have accomplished your goal. Here's my antiderivative, right? And I want to make sure that I switch back fully to the x variable because you should always be responding to a question in the variable that it was presented to you. So great, this is awesome. So kind of a non-traditional question. This would be a Calc 1 question, I threw it in here just because you're responsible for it. When you take a look at example 8, notice what I did there is I took off the numerator. This is a problem for us. This means you are not in a basic u substitution. This is not going to work out as a basic u substitution because I have nothing in the upstairs to cancel like I did in example 7. I'm going to have to come up with something else. And if I stare at this, nothing is really jumping out at me. I can't do a u substitution. You're not allowed to break up things in a denominator. Oh, that's terrible. I really don't have a lot to go on here. Those are the only 2 strategies I have. So out of my back pocket, I'm going to reach for something else. What I'm going to try to do is try to look at that denominator in a new way. See if I can rewrite that denominator's expression. And so what I'm going to pull out from a advanced algebra class or a pre-calculus class is I am going to, believe it or not, complete the square in the denominator. It sounds like a terrible idea, mostly because you might not remember how to complete the square. But let me tell you what I see here of why I want to do that. I'm going to write it. I'm going to try to complete the square. That's an old algebra technique. I want to transform that denominator and make it look different. What I notice about this integral is that there's no radical anywhere. So let me not make you dizzy. Close your eyes for a second. I'm just going to fly up here. What I notice about the integral is there's no radical. So what I'm trying to get is I'm going to try to get something like this. I'm going to try to make this an arctan. That's kind of like a shot in the dark here. Let me fly back. Close your eyes. and I'm going to do this. So here's what I'm going to do. I'm going to rework this integral. And I'm going to do it in a really weird way. I'm going to leave the x squared and the 4x. I'm going to leave myself a big space. And I'm going to move the 7 over here. And what I end up doing is I try to keep myself organized. I put these like weird little holders. I'm going to do stuff in there. I'm going to complete the square. So what that means is I want to try to have this written as like something squared plus a number. So here's what I'm going to do. I'm going to complete the square on this little like piece of the puzzle. And then I'm just going to deal with whatever happens here. Okay. So completing the square is you have a positive 1 coefficient on the x squared term. So check. I take the middle coefficient, that -4, I take half of it, which is -2, and I square it. And normally it's an equation. Normally I would say you add that to both sides. Well, look, I'm going to take half of -4, which is -2. I square it. That's a 4. Now, keep in mind, this is not an equation that we're dealing with. We are trying to rework that denominator. So I don't have another side of an equal sign to say, oh, I'll just add 4 to the other side. What I want to do is maintain equality. If I just added 4 magically into this denominator, I need to offset that and I need to subtract 4 because I want to make sure that denominator algebraically equates to x squared minus 4x plus 7. So what that has done for me, let's take a look. See if I have this like kind of grouped. What I want to do is factor that quadratic, and this is guaranteed to be awesome. When you complete the square, you can factor it into 2 binomials, but it's always going to be perfectly the same. See that? And then what I have with the numbers, I'm just going to do it, like whatever, 7 minus 4 is 3. So what you've just done, really in a really crafty way, is you have reimagined that denominator to suit your needs. By completing the square, you have made it possible to actually come at this and say, you know what, I did accomplish this goal. This is an arctan-ish looking derivative in here. How does that work? Well, u is x minus 2, and a is the square root of 3. So I'm going to do the follow through, right? I always do a follow through whenever I'm changing to a u variable, but I have actually morphed that integral into something recognizable to me that I can work with. So what you've just done is you've just said, hey, instead of writing x minus 2 quantity squared, I'm going to say u squared. And instead of writing plus 3, I'm going to say a squared, because I said that a was root 3, so that works out wonderfully. And du is dx. Now, hold on to your hats here. If I kind of fly around, I have u squared plus a squared in that denominator. What do I have up here? I have a squared plus u squared. But remember, addition is commutative. Don't be hung up over like, well, this is in a backwards order. It's commutative, so it doesn't matter. If you want to switch it, go switch it. But you certainly do not have to, and I want to be clear about that. Okay, so my antiderivative in here, I'm going to get to it, because right now I have it morphed into like this perfect situation, and I'm just going to go for it. My antiderivative is 1 over a arc tan u over a plus c. I'm going to throw all my pieces of the puzzle in here. And I think that's a pretty good looking answer, but I don't know, maybe you have people that want to see things rationalized because we're all traumatized by rationalizing everything that we see. There you have it. Okay, so really non-traditional problem, really crafty way of using that prerequisite work from an advanced algebra class and allowing it to do something fancy. Okay, so that's great. Okay, now if I slide on to example 9, again, I don't want you to lose your mind here, but I always want you to consider a a basic u substitution first. So I'm going to do it. I'm going to say, you know what, let's try a basic u where I let u be the entire denominator. And anytime you do that, what you're really going for is you want your integral eventually to be 1 over u du, right? Now I'm going to do that here. I'm going to do the follow through, which means I'm going to take the derivative. Notice I had to chain e to the 2x, right? The derivative of e to the 2x is itself, but then the derivative of 2x is 2, so I chained it. So here is my follow through, which looks pretty promising, right? If I come at this and say, okay, I'm going to rewrite this integral. I have an e to the x. I let that entire denominator be u, so that's great. And then I have du over 2e to the 2x. My problem here is that I can't cancel them. Let me be clear again about, let's just switch all to blue here. Let's be clear. No, let me keep it. I'll keep it color-coded. E to the 2x you can write like this. I'm just getting into some like basic algebra nonsense, right? Because I can see that e to the 2x is x plus x. You can break it down like this, right? So what's happening here is the u substitution, thought it was a good idea. You can get rid of one of the e to the x's, but you can't get rid of the other one. And so because this guy is kind of hanging out and I have no way to address that problem, then, hey, this was a great idea, but I'm just going to cross it out because it doesn't work. Okay, so it wasn't a silly idea, it wasn't a bad idea, it's just an idea that did not shake out for me correctly on this problem. What I then need to do is come up with some other way of addressing this problem, right? So you can view, it's so interesting, you can view e to the 2x, let me just write all this down, as e to the x plus x, or e to the x times e to the x. You can also view e to the 2x in a couple of different ways, which would be e squared raised to the power of x, because that's where you multiply exponents, or you can view it like this. You can view it as e to the x squared. So I just want to be clear about like how I'm handling this e to the 2x. There's lots of ways of viewing it. You can view it as e to the x times e to the x. You can view it as this. All of these are equivalent statements. This is the guy I'm going to latch onto here. So let me go back up. Let's go back up and say, look, let me reimagine what's going on here. What if I write e to the 2x like this? What's happening here is, again, I don't see a square root anywhere. I am going to really try to morph this into an arctan derivative in here, which sounds like a crazy idea, but I don't have anything else to try. I'm just going to be honest here. So I'm going to try to morph this into an arctan situation. So I'm going to put arctan question mark, right? So I'm going to say, well, how would I do that? A would be 1, and u, that looks terrible, u would be e to the x. Now my follow through would be, let me take the derivative. All right, how is this going to look? Well, I'm switching this around. I've got this integral. I didn't really do anything with the e to the x in the numerator. I kind of ignored that part. But what I have in the denominator is I do have a squared and I have a u squared. And by the way, I have this follow through here. Let's keep in mind, what am I going to replace dx for? I'm going to replace it for du over e to the x, which happens to be the magical moment that I was hoping for. That e to the x that I kind of ignored in the numerator does eventually wash out with that du follow through. So this is amazingly awesome. You have morphed this whole thing over to be perfectly the derivative of arctan, and I'm going to run right for my antiderivative then, because it's 1 over a arctan u over a plus c. So I don't have to write 1 over 1. And what do I have? E to the x over 1. I'm just going to say arctan e to the x plus c. Done. This is really interesting, but I don't want you to lose your basic u substitution ideas. So that's example 9. Very non-traditional, very, very quirky, right? All right, so here we have our our next example, which kind of looks like an arc sine, but you have a lot going on in that numerator, and so, I have more than I want. If only I didn't have that x there, that would be awesome. If I could just, like, I don't know, let's see if I could, like, if I could just cover up that x, if I just had 2 over the square root of 4 minus x squared, that would fit to an arc sine, because that would be numbers squared minus a variable squared all under a radical. So this could be arc sine. But I can't just change the problem. Let's be honest, right? That doesn't work. I do see an x there. I can't just cross it out. But let me go on the flip side. Let me think about something else. What if I didn't see the 2? If you don't see the 2, this is a basic u substitution that you kind of already handled a problem just like this. Let u be the entire denominator, well, the inside part, 4 minus x squared. Its derivative is linear. It's negative 2x. I've got an x up there. This is great. So, like, you just have too much going on in the numerator, but here's the thing. Legally, you can handle this problem. You actually can tackle this separately, and it's legal to do so. We have done this before. I can't remember what problem it was, but you can say, look, I see this nice expression all over a common denominator, but what I want to do is separate it. This is legal. Now again, most of your math life in your advanced algebra classes were spent doing things like, hey, take this expression and simplify it. Like you're trying to take 2 fractions and condense it down to 1 fraction. Notice here I'm sort of going the other direction. I'm blowing it up because now I can handle them individually. I can come at this and say, you know what? I can handle this as an arc sine problem. And you know what? I can handle this as a basic u substitution. And that's legal. This is algebraically legal to address this problem this way. So you have 2 separate integrals. Remember, you're allowed to do them piece by piece, term by term. So you have 2 different strategies going on in the same integral. Totally appropriate, totally great. I'm going to do it. I'm going to say, on my basic u substitution, your best choice of u is something inside a composite function. I'm going to go through all of my follow-through, including setting the dx by itself. So what this means is my integral, well, I had x, I had square root, and then I let that whole entire thing underneath there be u, and then instead of dx, I'm going to write the equivalent, which is du over negative 2x. This is great because, again, the x's are gone. That's lovely. I do have a negative 2 in the denominator. I'm just going to pull that out as a coefficient. And I'm really integrating u to the negative 1/2 power. I need to use the power rule for integration, and so this does it. So let me just go all the way to the finish line here. I'm kind of there. I'm going to add 1 to the exponent. I'm going to divide by 1/2, which is the same thing as multiplying by 2. And then I have this negative 1/2 in front. And again, I might as well just keep on going. Let's just cut out those 2's. And switch back. I'm actually going to go to radical form here if you guys are okay with that. Okay. So I've got half my antiderivative accomplished, right? I need to get the other half. I need to come at this arc sine problem, right? How am I going to tackle this? So I'm going to say that a is 2. I'm going to say that u is x, and I'm going to do the follow through. And so I have a similar approach here. I'm going to come at this integral that I had. And I'm going to kind of work this out where, like, yes, I have a square root. That's great. And I have a squared minus u squared. And instead of dx, I'm going to write du. This is great because I can pull the 2 out of the integral. And now I have the perfect scenario for arc sine. My antiderivative happens to be, well, 2. And then I have arc sine of u over a plus c. So what does that mean for me? I'm just going to kind of drag it down here. I have an extra term to my antiderivative, which would be x over 2 in the arc sine, and I am going to box this up. So that's my final answer to this integral. Notice I used 2 different strategies. And that's appropriate. Once you get a term by term, you're allowed to do this, you know, and don't be like annoyed. Like here you let u equal 4 minus x squared, but here you said that u was x. These are almost like two totally separate styles. You're handling each piece of the puzzle independently. Okay, so, you know, we're getting a little more involved. Now, the reason I ended with this last problem here is because, again, I wanted to sort of tie this up on how I started. We do not know the antiderivative of arcsine. It is not something that we are going to address. That is not what this section is about. It is about recognizing the derivative of arcsine as your integrand. Now, this is an interesting one, but now we have the skills to do this. Again, this could not have been in a Calc 1 course. This is too fancy. In a Calc 1 class, you couldn't address this. But what I'm going to say about this is, look, I see an arcsine. I also see the square root of 1 minus x squared, which is kind of like the derivative of arcsine. This is great, okay? So what I'm going to do is I am going to handle this as a basic u substitution. It kind of fits here because, well, we're sort of putting a lot of ideas together. What am I going to let u equal? Well, I'm going to let u equal arcsine, mostly because I don't know what the integral of it is. But I definitely know the derivative. And it's great. And I'm in a basic u substitution. I'm going to solve for dx, and so I'm going to kind of algebraically morph this together. So dx is going to be replaced with the square root of 1 minus x squared du. Okay? So I'm going to come at this, and I'm going to translate it over. What have I done? I have to kind of think about what I let u equal. So I let u equal arcsine. I did not mess with that denominator, right? I kind of left it alone. But it turns out that when I do my follow through here, right, if I keep my colors correct, instead of dx, I'm going to write square root of 1 minus x squared du. This is exactly what I was hoping for. Those go away. You have totally converted this integral over into something that is possible to do. This is a power rule. So what I'm going to do is I'm going to use my power rule integration, right? I'm going to add 1 to the exponent, divide by my new exponent, and slap a plus c on it. I can't box my answer up because my integral was in terms of the x variable, so go for it. This looks amazing. You can write it like this. You can also, of course, just pull that 1/2 out as a coefficient, whatever looks good to you. Okay, so I just wanted to throw that in there, that this is kind of a nice culmination of a lot of the ideas that we've been talking about in this unit. All right, so this is our last lesson. You got to kind of put everything together from all of these video lessons and get ready for your Unit 1 test.